Young's modulus, also known as elastic modulus or the modulus of elasticity, which is a physical parameter that reflects the mechanical behavior of any materials in response to the induced stresses due to the loading. My name is Jagadish Atole, and in this video we will discuss about the Young's modulus or modulus of elasticity. Do subscribe the channel and press the bell icon so that you never miss any new learning video from the Designgekz. Without any further delay, let's deep dive into the topic. Young's modulus is one of the three main elastic constant along with the shear modulus and bulk modulus, which is used to describe how materials deform under loading. Before jumping to the modulus of elasticity, let's understand the elasticity first. When we hear the word elasticity, the first picture comes to a mind is something like spring or the rubber band or the sponge ball. But is this really what elastic means? The answer is no. Let's take an example of spring. When the compressive force or the tensile force is applied on the spring, it changes its shape and size due to the tension and compression. The force which is responsible for this change is referred as a deforming force. And the ability of these materials to regain its original shape and size when the deforming force or the applied force is removed is called elasticity. Another example like a rubber band and sponge ball, which shows the elasticity when stretched or compressed, they get deformed, but they soon return to their original shape. And this self-reversing deformity the object goes through when the force is applied to it and removed is called the elastic deformation. But is there any limit of elasticity of an object? Do elastic objects may remain elastic for forever, or do all the materials show the same elasticity? Not really. When we stretch the material up to the elastic limit, it will come to its original position after removal of the load. But if we stretch the material beyond its elastic limit and released, it will not be the same as before. It will show a slight change in dimensions, means it goes into the plastic deformation. That is, the material or object is no longer elastic. And if we keep on stretching it, or if the stretching force is excessive, then it shows the permanent deformation and may even break. Hence, the elastic object does not remain the elastic for forever. It goes into the plastic deformation. Now let me ask you one question. Suppose we have the string made of rubber and steel. Both are having the same dimensions. Both are of same thicknesses. Now if we stretch both the string with equal and opposite force with the tensile force from both the end, then which will stretch the furthest, assuming the deformation is elastic in both the cases? Obviously, rubber string will get stretched furthest and the steel string will get barely stretched. So the question is, which is more elastic, steel or rubber? The answer is steel. Steel is more elastic than the rubber because the steel string doesn't stretch as far as the rubber string, and this is because the steel applies more resistance to the deforming force than the rubber. Now, another definition of the elasticity is that the property of the materials which opposes the deformation or the ability of a material to resist any permanent change to it when the stress is applied is also known as the elasticity. With this, we can say that the steel is more elastic than the rubber. Moreover, as soon as the force is removed, the steel string regains its original shape and size faster than the rubber string. That means, with the general definition of the elasticity is that the ability of a material to return to its original shape and size after the removal of external load is also called as the elasticity. By this definition also, we can say the steel is more elastic than the rubber. Now, this can be experienced with the application of the force within the elastic limit in another direction like this. So from this experiment, we can find that like after applying the load in this direction, it will bend the part of the rubber string like this and the steel string like this. And when we release the force, it will come to its original position. The steel string will come to its original position faster than the rubber string, and the rubber string will be in a deflecting condition for a long time after the removal of applied force. Now there is a general misconception that a lot of us have about the elasticity. We think more the object gets stretched or compressed, the more elastic it is. But the elasticity is not same as the flexibility. In physics, we say A body is more elastic if it offers more resistance to the deforming force and quickly return to its original shape after the removal of force. And as the steel offer more resistance and quickly return to its original shape and size after removal of force, it is more elastic than the rubber. Now, to define this elasticity more technically, the scientist Thomas Young gives the constant which we now call as Young's modulus, and it is the measure of an object's or the substance resistance to being deformed elastically when the stress is applied to it. Now, the Young modulus qualifies the relationship between the tensile stress or the compressive stress and axial strain in the linear elastic region of a material. So, from this stress strain diagram of the materials, the Young's modulus is the slope of stress and strain. So, we can consider the slope of stress to strain for a material under the tension or compression. So, the Young modulus is stress upon strain. Now, we know Hooke's law, which states that the strain of the material is proportional to the applied stress within the elastic limit of the material. Means, in short, we can say the stress is directly proportional to the strain within the elastic limit, and mathematically we can write the stress is directly proportional to the strain. Now, if we put the constant at proportionality, we will get stress, which is like sigma is equal to E into the strain epsilon. Now, this E is the modulus of elasticity or the Young's modulus. Now, from the above equation, we can write E is equal to, or the Young's modulus is equal to stress upon strain. Now, if you put the values or the formulas for the stress, it will be E is equal to F upon A, that represents the stress, and for strain, it is the change in length upon the original length, that is delta L upon L. We can write it like this also, like E is equal to FL upon A delta L. And here are some values of the Young's modulus for some materials. The Young modulus is generally expressed in megapascal or gigapascal. Here in the table, the values are mentioned in the gigapascal. The rubber is having 0.01 gigapascal to 0.1 gigapascal. For nylon, it is 2 to 4 gigapascal. For steel, it is 200 gigapascal to 210 gigapascal. For aluminum, it is 69 gigapascal to 70 gigapascal. Now let's take one numerical example for Young's modulus. The question is to calculate the Young's modulus for the materials of the bar shown below. The bar has an initial length of 400 mm and it is measured as like extend by 0.22 mm under a tensile load of 75 kilonewton, and when the force is released, the bar returns to its original length, means it is in elastic limit. The bar has the rectangular cross section as 25 mm by 20 mm. Now we need to calculate the Young's modulus. Young's modulus is equal to stress upon strain. If you put the formula for stress and strain, it will be E is equal to F upon A divided by delta L upon L. If you rearrange it like this, you will get FL into A into delta L. So we know the values, like F is equal to 75 kilonewton. Convert that into the Newton, it will be 75,000 Newton. Length is 400 mm and the delta L is 0.22 mm. Now if you put the values in the formula, we'll get the value for the E in Newton per mm square, and if you convert that into the gigapascal, we'll get E is equal to 272.72 gigapascal. Now let's summarize the Young's modulus. The Young's modulus is the slope of stress and strain within the elastic limit. The Young's modulus is also referred as elastic modulus or tensile modulus or the modulus of elasticity. And the elastic modulus is the measure of the stiffness of the material. In other words, we can say the elastic modulus is a measure of how easily any materials can be bent or stretched. Now, the greater the value of Young's modulus, the stiffer is the material. That means hard materials will have high modulus of elasticity and the flexible or the soft material will have the low modulus of elasticity. And the scientist Thomas Young said that the value of elastic modulus depends on the material, not on its geometry. Means the small piece of rubber or the large piece of rubber has the same elastic modulus. In general, the Young modulus is the measure of an object's or substance resistance to being deformed elastically when the stress is applied to it. And the Young modulus is used to derive the relationship between the stress and strain. And Young modulus is an important design parameter used for computing the elastic deformations, and it specifies the materials by how much it can extend or shorten under the tension or compressions. So this is about the Young's modulus. Stay tuned with the Designgekz for more learning videos. Thank you.